So if we go back to last time, what did we talk about? And we spent a big chunk of our time talking about sort of two things, and they go together. So it's these two pieces here. Namely, when you have this, this u, that's the unit step function, think of that as your on-off switch. It really comes when you have things where there's changes in behavior, if you like piecewise functions. So if you have u of t minus a times f of t minus a, essentially what you've done, if you think about, not even looking at what's happening over here, if you think about what this is saying, it's saying take your function f of t, but shift everything over a units. So that's what this t minus a is doing. It's saying, well, shift everything over by a. But you don't even start until time a. Well, that shifting over corresponds to the e to the minus as. So the punchline is that whenever we see an e to the minus as showing up, after our Laplace transform, that came from a shift. And if we're doing the inverse Laplace transform, we have to make sure we account for a shift. And the other thing was this delta function. And the delta function, remember, is a function where it's like everything that matters happens at a. That's all I care about is what's happening at time a. And so it's supposed to capture things like sort of momentary pulses. Like it likes to use the analogy, you hit something with a hammer, and you have that whack. And you hit it, and it affects it. So, and well, what happens after that to your system? And the thing is, when you transform, you get e to the minus as. Now, as far as us, when we will see delta, we'll only see delta in the setup of problems. And that is that it's capturing some sort of a pulse or impulse function is sometimes what the book refers to it as. And when we transfer over, it'll show us e to the minus as. Then when we do our algebra and pull it back, by the time we pull it back, we won't ever be pulling back e to the minus as. There'll be something that's been attached to it. So that delta functions become these unit step functions at the end. All right. Well, practice. That's what we need. Practice. So, use Laplace transforms to solve x double prime minus 2x prime plus 5x equals 2 delta t minus 3, x of 0 equals 0, and x prime of 0 equals 1. Now, on this problem, we should use Laplace transforms. And I say there are two reasons why we should use Laplace transforms in this problem. Can you give me one reason why? Yes, very good. It says it. When it tells you to use Laplace transforms, you should use Laplace transforms. Now I'll tell you the other reason. Even if it hadn't said use Laplace transforms, when you see the delta function, the only time that we'll encounter the delta function in our course is when Laplace transforms are involved. So the delta function is a signal, hey, Laplace transforms are going to be used. Okay, so if we're solving something by Laplace transforms, where do we start? Yeah, we start by saying, okay, the basic idea is we're going to take this equation. It's currently an equation in terms of t. We're going to take the Laplace transform of both sides, turn it into essentially an algebra problem involving s. So we'll take the Laplace transform of both sides. Laplace transform of x double prime minus 2 Laplace transform of x prime plus 5 Laplace transform of x. This is using the fact that the Laplace transform is linear, so I can break up over addition and subtraction, and I can pull constants out, equals to Laplace transform of delta t minus 3. Okay, and now we're going to go through term by term and figure out what's happening. So, what's going to become Laplace transform of x double prime? Oh, sorry, what? Okay, so we go to our sheet. We know how to handle the second derivative. S squared, the function, goes into x of s. What happens to this term? 0. we use initial conditions. And so then minus the derivative at 0. So this will become, as people said, s squared x of s minus 1. Okay, so that's the first part. And now we go to our second part. What will the Laplace of x prime become? S times x of s, and the f of 0, or x of 0, goes away, because initial conditions. So notice one of the things that you see when we have the Laplace transform is our initial conditions actually come in right at the start. See, normally in the past when we solved problems, our initial conditions came at the end. So we've sort of turned it around. The last part, what will that be? Yeah, 5x of s. Okay, and we're most of the way done, but just to finish it up and just to show you how many different markers I have, showing off my awesome collection here. All right, the Laplace transform of delta t minus 3. What will this become? Yeah, e to the minus 3s. All right, good. All right. With the 2. See, that's why I left that suspicious space there. Okay, good. Good. All right. Well, we've done sort of the first step where we said, hey, we take our differential equation, apply the Laplace transform to both sides, we get something involving s. Where do we go now? Okay, solve for x of s. Get x of s by itself. Okay, so for instance, when I look at the x of s, I see there's 3 terms. So we can just put those together. S squared minus 2s plus 5 x of s. And it's not really that surprising that we see that kind of polynomial showing up. We've seen that happen multiple times this semester. What will that equal? Yeah, don't forget about that 1 there. Move it to the other side. Isolate 1 plus the 2e to the minus 3s. Okay, and we're solving for x of s. Okay, so we've got to get the x of s by itself. And I'm going to actually just think of it, I'm going to divide each piece by this part. So 1 over s squared minus 2s plus 5 plus 2e to the minus 3s s squared minus 2s plus 5. All right, well, our goal is, at this stage, we want to be thinking ahead and saying, well, we want to do the inverse Laplace transforms. And the way we do inverse Laplace transforms is we come to our table and say, hey, I recognize this as something on the table. So what we need to do now is say, can we rewrite these expressions so that it's like, oh yeah, I can point to this part or I can point to that part. I mean, there's some place on the table we can point to. So what do we need to do now to help us get to that point? All right, there's some. Complete the square? Why not just factor? Ah, that's sad news. All right, we've been told it doesn't factor. All right, so complete the square. All right, but nice thing is, completing the square you can do. And the way you complete the square is you just start s squared minus 2s, and you ask yourself, what would we need to add to make it a perfect square? Plus 1. And because the way you get that minus 2 divided by 2 is minus 1, and you square that. Well, I have plus 5, so what's left over? Plus 4. So it's really s minus 1 squared. We can write it as 2 squared if you like. So 1 over s minus 1 squared plus 2 squared. And I'll bring this e to the minus 3s out in front of it. I'll even bring the 2 out. 2e to the minus 3s, 1 over s minus 1 squared plus 2 squared. All right. Now we go back to our table. And we start saying, okay, does anything on our table remind us of that? Well, sorry, what was that? Well, okay. Well, there's a couple things. It vaguely looks like sine, right? Because sine, you have something squared plus something squared. Variable squared plus number squared, number upstairs. What's bad about the sine, though? What's off? There's a shift here, and there's something else. There should be a b on top. Well, the thing on the top, that's easy to fix. What would we really want to be on top? Okay, we'll put a 2 there. See how easy math is? If you want something, you just put it there. Well, okay, it's not quite how math works. But if we put a half, then we're okay. All right, so we got the 2. There's the shift, but how do we handle shifts? So this rule is how you handle shifts. So whenever you see shifts, that corresponds to having multiplied by an exponential function. So here we shifted by 1. So we should say it should be a sine of 2t and e to the t. Yes? Okay, all right, good. Confirmation, yes. Now, that's good. Now, the second one, we're just going to move this 2 back on top. So we're ready to write down our answer. So x of t, so we already figured out that this part is going to go to e to the t sine 2t. If the sine of 2t would be 2 over s squared plus 2 squared, the e to the t shifts it, so it becomes s minus 1 on the inside. And then we're going to add something. So let's talk about this second part. And we actually recognize this part. We know what this corresponds with, because it's the same as what we did over here. So we can do some comparisons. By itself, this should go to e to the t sine of 2t. That's the right function to do that. But then you have this e to the minus 3s. What effect does that have? So whenever you see e minus as, that's this part here. And in particular, it corresponds to this u function, and really corresponds to shifts. And so this says we should really shift everything by how much? By 3. So when I talk about shift, I mean we're going to turn it on at time 3, and we're going to treat it as though the function were to start at time 3. So we're going to have this u come into play. So our answer will be u t minus 3. So that says, okay, we're starting this behavior at time 3. And then we're going to take our function, and it's going to be the same function. We're just going to shift everything by 3. So t minus 3 sine 2 t minus 3. So this is our u of t minus a, f of t minus a. We can rewrite this slightly. Can we? Not really. Yeah, this looks great. So I was thinking maybe we could do something here, but no. It's what it is. So, and there we go. Okay, that's it. Beautiful, right? So the process, no big surprises. Apply Laplace transform, do your algebra, put things into the right form where we use our table, and do the inverse Laplace transform. And recognize that when you have things like e to the minus as showing up, we're going to have shifts. So we should anticipate if we see a delta function happening at time 3, something happens to our answer at time 3. And that's what we see happening here. All right. Are we satisfied with that? Can we do another one? Yes. All right, good. 2 questions, the same answer. Next example. A mass of 1 on a spring with constant k equals 4 starts with x of 0 equals 3 and x prime of 0 equals 0. And then at time 2 pi, the mass is hit with a hammer. And it's going to provide an impulse force of 8. So in other words, there's this external force that happens. It's an instantaneous force that kicks in at time 2 pi. And when I say kicks in, it just for that one moment, there's an impact. And so we can model this. X double prime plus 4x is 8 delta t minus 2 pi. So the delta just says only at that one instant something interesting happens. And our goal is solve for x of t. And you might say, well, what's really happening here? Now before we start, we can actually draw and get a good sense of what should happen. So notice it says x of 0 equals 3, x prime of 0 equals 0. So what it is you came and you pulled your spring and stretched it to 3, and there's no velocity. It's just at position 3, and you release. So if you release your spring, what's going to be happening? What does the spring do? Yeah, it goes bouncy, bouncy, bouncy. It does a spring thing, right? So it's going to go do. Okay, it'll go down as far. Okay, I'm going to here's my new 0. All right, so it does this for a while, and then all of a sudden at time 2 pi, you come along and you smash it with the hammer. Well, maybe you don't smash it. Lovingly tap it. Boo! Well, what'll happen? Well, it'll change the spring a little bit. So maybe it'll do something like this. But it's this one moment at time 2 pi that something happens. So we should really think of there's going to be before 2 pi and after 2 pi in our final answer. All right, well, let's just run through it. Same ideas. So first step, take Laplace transform. Laplace transform x double prime plus 4 Laplace transform of x equals 8 Laplace transform of the delta function t minus 2 pi. All right. Let's go through it term by term. Laplace transform of x double prime. We can always use our sheet. What will this become? Okay, s squared x of s. X is 0 equals 3, so minus 3s, and then 0. Okay, good. So s squared x of s minus 3s. Plus 4 Laplace transform of x of s equals 8 Laplace transform of delta of t minus 2 pi e to the minus 2 pi s. So the delta function, super easy to take Laplace transforms of. So we don't mind seeing that on our problems. Okay, where do we go? What's next? Solve for x of s. So we can say s squared plus 4 times capital X of s. We'll move the minus 3s to the other side. So that equals 3s plus 8 e to the minus 2 pi s. And now we can divide. So x of s is 3s over s squared plus 4 plus 8 e to the minus 2 pi s over s squared plus 4. Pull out our table. Let's look at these pieces here. The 3 is a constant. We don't need to worry too much about that. we have s over s squared plus 4. Does that match anything on our table? Yes? Matches the cosine, right? So that's pretty good. In fact, I'm just going to pull the 3 out in front. So s over s squared plus 4. The next piece. Well, the e to the minus 2 pi s will come out in front. So that just is going to tell us, whenever we see e to the minus 2 pi s, we know that's going to correspond to this unit step function on-off happening. So we know that automatically. We just have to figure out, well, what's turning on and off? So 8 over s squared plus 4. What does that look like? Looks a lot like sine. Someone said 4. Because what? Well, what do we want upstairs? We want 2. Because we have 2 squared is our b squared, right? So we'll pull out 4. Then we'll have 2 over s squared plus 4. All right, so we'll just make a little tiny note underneath here. This by itself should go to cosine, and this would be sine. Now that's before we take care of the shift. All right, so now we're ready to write our answer. So x of t. So would be 3 cosine 2t. That one's no surprise. What comes next? Okay, we can write the 4. Because we have the c to the minus 2 pi s, that we know that there's the u, t minus 2 pi. Something happened at 2 pi. And what happens at 2 pi? The sine of 2t switches on. So it's sine, but it's not sine of 2t, 2t minus 2 pi. Now you might say, but wait a second, Steve, hold on. Maybe it is sine of 2t. Well, it might be able to reduce to that, but we always start in this form. If you look, this is the same as 2t minus 4 pi. What effect does the minus 4 pi have to that sine function? None. Because what's happening, minus 4 pi says go around the unit circle twice in the wrong direction, the minus. But if you go around the unit circle twice, you're back where you started. So this is a perfectly valid answer. And this is also a perfectly valid answer, namely 3 cosine 2t plus 4 u of t minus 2 pi sine of 2t. They're both right. There's another way we could have expressed our answer. And I just want to emphasize that when you see things involving this unit step function, it really means piecewise. So you could have done it piecewise. And we say, okay, something happens at 2 pi. So we have before time 2 pi, and then we have after time 2 pi. So before time 2 pi, what do we see? 3 cosine 2t. The second part hasn't turned on yet. After time 2 pi, what do we see? Yeah, the 3 cosine 2t plus this part is now contributing. So that's what we'll see. And that matches with the idea that says, hey, initially you see one type of springy-like behavior, that 3 cosine 2t. Then you nudged it with your hammer, and you got a new behavior. So this is actually a different behavior. So for instance, you can talk about how high up and down can you go. So here, you go between 3 and negative 3. All right, do we have any trig fans? Can you tell me how high up and down I go afterwards?
Just one because they don't cancel each other?
Well, sometimes they cancel, sometimes they combine. And the answer is 5. You're like, whoa, where did 5 come from? The square root of 3 squared plus 4 squared. So that extra nudge causes the spring now to go up and down a little bit higher than it did before. And so that's what we have. All right, good. And now which answer is the correct answer? They all are. So on a test, you could put any of them. I like this one. It really helps emphasize the piecewiseness of it. So I'll put a box here. I have to put a box somewhere. Now, there was a question someone asked in the other class today, and I think it's a good question. It says, do we really have to do these problems piecewise? Oh, actually, no. I don't want to answer that one here. I want to do it on the next one, because the next one is more interesting. The delta function, if you see delta function, you got to do Laplace. But here, we'll do another spring problem. You know, it doesn't feel like a differential equations class if we don't do a spring problem every couple of weeks. All right. Slightly different setting. Still have a mass of 1. Still have a spring constant of 4. But now, we have our spring starting at 0 and derivative is 0. So what does that tell you about the spring initially? It's at rest, right? It's not moving up and down. It likes where it is. Okay. But there's an external force acting, and that force is cosine 2t. And that force doesn't go forever. It just acts for a little bit of time, from time 0 up to 2 pi. And then, after time 2 pi, the force stopped acting. And now, solve for x of t. Okay. So, that's the problem. All right. Well, what's a little bit different about this problem versus the last two problems that we've done? Oh, okay, so we have some functions, right? There's something else that's a little bit different about this problem versus the other problems. We don't have an equation. If you look back at the previous two problems, it's like, hey, there's an equation. Or here's an equation. And now we're like, oh, they didn't give us an equation. So this is the fun, like, ooh, we get to figure out the equation stuff. Okay, good. So now we do the equation. And how does it work? Well, there are sort of two pieces here. There's two sides. And one side is the external force side. And so we have to figure out what that is. And the other side is the spring stuff, which we'll write as spring stuff. All right. Which side do we want to start with? Spring stuff? Okay, what goes over here? Yeah, x double prime. So this is, you can think of it as really 1 times x double prime, mass times acceleration, that's a force. And then there's Hooke's law. That's where the 4x comes in. And there's no dampening going on, so there's no x prime term. Okay, so that's our spring stuff. What's our external force? Okay, so I think we can agree there's a cosine 2t. But does that capture everything? No. Because what's happening is that our external force has really two pieces. There's up to time 2 pi, and there's after time 2 pi. Before time 2 pi, that's the cosine 2t, which we've already written. And then it says after 2 pi, the force is turned off. So after 2 pi, what should we have? 0, because there's nothing acting. So this is okay initially, but then we have to somehow turn it off. How do we turn something off? We add 0? Well, if you add 0, that's not quite enough. We want to make it 0. Okay, so we could subtract cosine 2t, but if I just write subtract cosine 2t, what happens? It's always 0. So but I wrote it down, so there's probably something that we can do here to recover. What? Well, Well, not delta. Delta function only lasts for an instant. We need something that will be permanently off. The unit step function. So think of the unit step function as an on-off switch. So what's going to happen here is before time 2 pi, this last part, we won't see it. So we'll just see cosine 2t. After time 2 pi, we'll see cosine 2t minus cosine 2t, which is 0. Okay, so we're happy. Good. So that is our differential equation. All right. Now, are we ready to take Laplace transforms? And why not? A lot of it we're ready with, right? X double prime, the 4x, the cosine 2t. These are all things we like. And you say, well, he's pointed to that, he pointed to that, he pointed to that, and then he stopped pointing. So it's probably something over here. What don't we like about that expression? So if we compare, we want this thing, here's our u of t minus a, we want this to be a function of t minus a in order for us to properly apply the rules. And we're gonna be proper here. We're not gonna cheat. You know, we're not art history, we don't cheat. Sorry. No. I'm sure they're all ethical people who take art history. Okay, so we want to rewrite this part here. So how do we rewrite it? Well, the way we do it, it's not very complicated. The way I like to do it is just, I'll replace t by t minus 2 pi plus 2 pi. It's the same thing. But now we'll clean up. So this is u of t minus 2 pi cosine of 2 times t minus 2 pi plus the 4 pi. And now we ask ourselves the question, what does this 4 pi do to the function? Nothing. So the good news is it's going to be very similar. So it's cosine 2t, and I'll rewrite it as u of t minus 2 pi and cosine 2 times t minus 2 pi. So, but now we're in the right form to apply the rule. Okay, good. So, here we go. Laplace transform of x double prime plus 4 Laplace transform of x is going to be the Laplace transform cosine 2t minus the Laplace transform u of t minus 2 pi cosine 2 t minus 2 pi. Term by term, let's work our way through it. I think we can do this maybe in our heads now by this stage. What does the Laplace transform of x double prime become? S squared x of s. And our initial conditions being 0 says, okay, the other terms are going to be 0. All right, that's great. How about this for Laplace transform of x? Plus 4x of s equals Laplace transform of cosine 2t. We probably don't have that one memorized, but we can just grab it here. Cosine 2t becomes s over s squared plus 4. Okay. And now the last part minus this u of t minus 2 pi e to the minus 2 pi s, right? So if we see that u of t minus a, e to the minus 2 pi s, so e to the minus 2 pi s, and then the cosine 2 of t minus 2 pi really says we have to say what is f. See, this is this f of t minus a really says should become f of s. Where say what's the function cosine 2t become? Well, we know that it's right there. So we have s over s squared plus 4. All right. So far, I think we're doing okay. What comes next? X of s by itself. It's not too bad, right? We can factor an x of s out and divide both sides by s squared plus 4. And we'll get x of s is s squared plus 4 squared. That'll be interesting. Minus e to the minus 2 pi s over s squared plus 4 squared. Now the good news is these are the same thing. So if we figure out what happens with one, we know what happens with the other. So we grab our table and we start saying, please let there be something where there's an s squared plus 4 squared downstairs and there's an s on top. Please, 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 please. Ooh, t sine. Oh, it's so close. Yeah, it's really close. Really close. What do we need to make it this? 2b or something else? Yeah, no. We need the upstairs has to have that 2 times b term. In our case, b would be 2. So what do we really want up here? 4. So we just put it there. And of course, we balance it. And we'll do the same thing over here. So we'll have a 4 and times by a 4th. Okay, so now we're ready to write our answer. Okay, so here we go. X of t. So we have the 1/4. And this part, we already said, is set up for this t sine bt with b equals 2. So, t sine of 2t. And what comes next? Okay, minus 1/4. U, we should have that. We have the u because of whenever we see e to the minus as, there's that u function. U of t minus 2 pi. And then what? Yeah, t minus 2 pi sine of 2 times t minus 2 pi. So if you say, hey, that looks a lot like that, except we replace t by t minus 2 pi, you are correct. Because that's what we did. So if you think about the rules, this first part, here's our u of t minus a. This second part, this is our f of t minus a. And here, this would be our f of t for comparison. So it's the right rule. Now this is the right answer. But let's clean it up a little bit. A couple of things that we can do. This part right here, let's just make some notes. This is the same as sine of 2t minus 4 pi. And as we've said many times today, this 4 pi has what effect? None. Yeah. So we can write this as 1/4 t sine 2t minus 1/4 u of t minus 2 pi, t minus 2 pi. Oh, I did not plan this well. Sine, oh, come on, 2t. Okay, I'll say that fit. All right. Just barely, just barely. All right. That's a perfectly fine answer. We can also do it piecewise. So let's talk about our pieces. So x of t equals, where do we make our dividing line? 2 pi, because that's where we turn the switch. So we have stuff that happens before 2 pi. We have things which happen after 2 pi. Now you might say, why do you always start at time 0? And that's inherent when you do Laplace transforms. Laplace transforms only care about 0 onwards. If you remember the definition of Laplace transforms, it'd say the integral from 0 to infinity. And so you don't see anything in the past. But in terms of physics problems, which oftentimes that's what we care about, that makes sense. It's like, how do you start? Well, let me see what happens when you run forward. Okay, before time 2 pi, what's happening to the last part? 0. So we see it's 1/4 t sine of 2t. And so what we can see there, it makes, well, okay, let's finish the second part. After time 2 pi. Well, after time 2 pi, that term is 1. So we see a 1/4 t sine of 2t. Then you have a minus 1/4 t sine of 2t. So what happens to these 1/4 t sine 2t minus 1/4 t sine 2t? They zero out. And then you have minus 1/4 times minus 2 pi times sine of 2t. So you end up with pi over 2 sine of 2t. So in terms of the picture, this agrees with sort of what we think should happen intuitively. Initially, our spring is at rest. A force starts acting on it. So what should be happening to our spring if a force is acting on it? It should start to move. And as the force acts on it, we would expect for it to move higher and higher up and down. After the force stops acting on it, what should our spring do? Well, it should become periodic. So it's not going to slow down, it's not going to speed up, it's going to become springy. And that's what this is saying. So in terms of time, it says initially, for the first 2 pi, you're going to go up, and then after 2 pi, you're going to be stable. So it's doing something like this, where initially you go up, and then afterwards you remain stable. Now this may not exactly capture, but it's the flavor of what's going on. Okay. So there was a question that was asked in the other class, and this is one I wanted to point to. Do you have to do Laplace transforms for this problem? No, you don't. How would you do this problem if you didn't do Laplace transforms? Well, the answer is you'd actually not do one differential equation problem, you'd do 2. What you would do is you say, okay, we're going to start x double prime plus 4x equals cosine of 2t, with the initial conditions x of 0 equals 0 and x prime of 0 equals 0. And we would solve that up till time 2 pi. And then we'd say, great, now let's do a second differential equation problem where we start at time 2 pi. And we'll run that problem. Now you might say, you put some question marks there. Well, how do you fill the question marks in? So how do we get these numbers? Yeah, so the first part helps us fill in what those numbers should be. So we could have solved the first part completely, figured out what happened at time 2 pi, used those as our initial value, solved the next one. We would have gotten the same answer. But we would have had to basically do twice the amount of work. You might have noticed we didn't have to worry about what happens at time 2 pi and making things fit together. It does it automatically. And that's kind of this amazing thing. The Laplace transform captures it automatically. All right. Well, yes, you can always do more. Mwahahaha. Wait, which one was I going to do next? Oh, this one. Not that this one's important. I just like this one. So we're going to do it. All right. Find the inverse Laplace transform of s to the 4th minus 3s cubed minus 2s squared plus 5s plus 8 all over s minus 2 to the 5th. Oh, good times. Good times. Okay. And I claim we're going to finish this before time expires. I know you're skeptical, but okay. What do we need to do to start?
Partial fractions.
Yes, good. Partial fractions. Partial fractions. Partial fractions. Okay, so s to the 4th minus 3s cubed minus 2s squared plus 5s plus 8. All this divided by s minus 2 to the 5th. Okay, so what, according to the rules for partial fractions, what should we have?
A over
Uh-huh.
plus b over s minus 2 squared.
b over s minus 2 squared, sounds good.
C over
S minus 2 cubed, good. D over s minus 2 to the 4th, great. E over, and, oh yeah, we can stop. All right, good. Now what?
multiply.
Yeah, clear your denominators. So s to the 4th minus 3s cubed minus 2s squared plus 5s plus 8 equals a s minus 2 to the 4th power, b s minus 2 cubed, c s minus 2 squared, d s minus 2 e. Well, now we just got to solve for a, b, c, d, and e. What could be simpler? Let's just make good choices. Plug in 2. Okay, we've had a great suggestion if we plug in 2. All right, 16 minus a number. Okay, no, we can do this. So that's 16, 2 to the 4th. This will be 24 minus 8, so we're minus 32. We had 16, so we're up to minus 16. Plus 10 gets us minus 6, plus 8 gets us to 2. So plug in s equals 2, 2 equals e. All right, we got 1. Well, actually we got 2, right, because e equals 2. Okay, so do we have another good choice?
Look at the first term.
The what?
The first term of the equation. So like the only x to the 4th possible is a x to the 4th.
But then we'd have to keep doing more stuff. We'd have to do s minus 2 to the 4th. Do you know what s minus 2 to the 4th is?
No. You just look at the first term.
Yeah, I know. But then to keep going, we'd have to do s minus 2 to the 4th power. Well, then we know what a plus b plus c plus d is. Okay, so let's take a derivative. What are you like? Oh, it's like you hate taking derivatives? Come on, you love derivatives. I know you have a secret love for derivatives. Okay, what's the derivative of the left-hand side? 4s cubed minus squared 4s 5 equals 4a s minus 2 cubed 3b s minus 2 squared c s minus 2. Okay, anybody have a good choice here? 2. Okay. Well, 4 times 8 is 32. 9 times 4 is 36. So, okay, 32 minus 36, we're up to minus 4. And minus 8, that minus 12, plus 5, minus 7 equals D. Okay, what should we do? Wait, what?
Well, I just have a different idea. What if we, instead of like doing derivatives, if we subtract, like that this stuff, we subtracted d to the other side, couldn't we then factor out s minus 2? Or would that make it?
Well, we could. That would involve long division. So the question is, what do you prefer? Derivatives or long division? Okay, good. Good choice. You've chosen wisely. We've trained you well. Okay, so derivatives. Okay, what's the next one? 12s squared. 18s minus 4 equals 12a minus 2 squared. Okay, and plus 2c. Okay, well, is there a good choice? 2. All right. 48, 12 times 4. Subtract 36. 48 subtract 36 would give us 12. Subtract 4 is 8. Equals 2c. So what is c? All right. Take more derivatives. All right, I love that spirit. 24s subtract 18 equals, on this side, 24a times s minus 2 and 6b. Well, what should we pick? Let's pick it 2. Okay. Over here, we get 48 subtract 18. 30. That equals 6 times b, so what is b? 5. All right. Pick 0? No, you haven't learned the game yet. What's the game? Yeah, let's take a derivative. Woohoo! Yeah, I mean, at this point, it's pretty easy to solve for a bit. But, you know, in for a penny, in for a pound. 24 equals 24a. So what is a? Yeah, we don't even have to pick anything. But I'm going to pick s equals 2. Just because that's what we said. So this idea works if you have a large repeated root over and over and over and over and over. If you didn't have a repeated root, it's kind of a hopeless idea. But if you have a root that shows up many, many, many times, this is a nice idea. Now we're not done. But what we can now do is we can come through here and we can replace all of these values by the appropriate things. So we have 1, 5, 4, minus 7, and 2. So these look like s minus 2 to a power. Where does that fit in from our table? S minus 2 to a power. Okay, so there's like an e to the ct. Whenever you see like s minus something, and then what else do we point to? What pieces do we combine? Yeah, so we're going to combine t to the n with the e to the ct rules. Those two rules are going to combine. So in our case, since it's s minus 2, everything will have an e to the 2t. And then we just have to work with the powers. So before we do our inverse Laplace transform, so this is to the first power. So think of it as whatever the power is here, we want the factorial of 1 less upstairs. So 0 factorial, what would we like upstairs? Is what we want upstairs, which is 1. So we have that, so we're happy with that. So 1 over s minus 2. Here, 2, 1 plus 1, we want 1 factorial upstairs. What do we have now? 5. So we'll pull the 5 out. 1 over s minus 2 squared. S minus 2 cubed. So 2 plus 1, we want 2 factorial upstairs. We have 4. So we'll put s2 times 2 over s minus 2 cubed. 4, we want 3 factorial upstairs. What do we have? Okay, but that's okay. Minus 7, 6. You know, we see fractions sometimes. That's not the worst thing. And the last one? 4 factorial, right? This is 5 is 4 plus 1. We want 4 factorial upstairs. We currently have 2. How do we get up to 4 factorial? We need a factor of 12. So 12 times 24 over s minus 2 to the 5th. Now we're ready to write down our answer, even though we don't have any space for it. So x of t, 1 over s minus 2 would become what? E to the minus 2t. Plus 5, e to the negative 2t times t. plus 2. And this will become negative 2t t squared. Minus 7, 6. Negative 2t times t cubed. Plus 1/12. Negative 2t t to the fourth. And we did it.